Previously, when we went over this problem here with the moving conducting bar here and the loop around it that's adjoined to, we analysed the induced EMF in the circuit by computing the magnetic field forces on the mobile charges moving through here in the moving conductor. So as that moved, the force was causing the charges to move. We can also consider the situation from another viewpoint based on the changing magnetic flux through the circuit. So that's what we're going to look at here. So when the conductor moves towards the right, a distance ds, the area enclosed by the circuit, this is this area here, A, B, C, D, increases by dA. When it moves, this little bit of area then becomes over here. So this area here has been increased, and that area is equivalent to L ds. So you can see that the length is L, this is ds. So obviously as that moves, that then increases by that amount. Change in magnetic flux through circuit then is B times dA, and because L ds is dA, we can just replace dA with L ds. So the rate of change of flux is therefore ds by dt BL. Right, so we know that ds by dt is the velocity basically, so we can just replace that with a velocity. So that's V, and we got VBL. We've just seen that VBL equals the induced EMF E. This equation here states that the induced EMF in a circuit is numerically equal to the rate of change of the magnetic flux through it. To state this relationship in equation form, we need some sign rules. When we define the magnetic flux as the integral B dot dA, we pointed out the ambiguity in defining the direction of the surface dA for an open surface. We resolved the ambiguity for a closed surface with Gauss's law by making dA point always out of the surface. For an open surface with a boundary curve, we now can arbitrarily pick direction for dA. So what we'll do is we use the convention for the direction of dA as to walk around the path of current direction, turning counterclockwise. Our head will then point in the direction of dA. Now if the magnetic field lines point in the same direction as dA, then we count the corresponding flux as positive. When they pass through in the direction opposite to dA, the flux is negative. We can also define the electromagnetic force E as positive if, curling our fingers of right hand around the direction of current, our thumb points up, where fingers point in the direction of charges that move due to the EMF. So just to make that clearer, so in the diagram above, dA points out of page because the current is in counterclockwise direction. We know that the current's moving in this direction, so we're going to say we put our fingers in the direction of current. Our thumb then we're going to say is in the direction of this surface dA. Because the flux now is going in this direction and the current is moving in this direction, and A is pointing up, then the A vector that we've defined, we've just used the convention, and the B vector are in opposite directions. So if that's the case, then we say that the flux is negative. As bar moves out, the flux grows in magnitude, becoming more negative, so the rate that flux changes is a negative quantity. We know that E, because it's going around its clockwise direction, is positive, so we write that the electromagnetic force equals minus the rate of flux change. So that might not be that clear, but the sign rule will become clearer later on, and we'll come up with another way of making this even clearer. It's called Lenz's law. But if you follow the logic of that through, it does make sense, although it's quite hard to get your head around it to begin with. That allows us to do calculations to show us the direction of the current and the flux when we're trying to solve these problems.